Hi everyone, and welcome to GCSE Edexcel Geography Made Simple. Today we'll be covering topic 4, which is the UK's evolving physical landscapes. And our objective today will be to be able, obviously, to identify the characteristics and distribution of different rock types across the UK. So in geography, we study both human and physical geography. And in this case, we will be looking at physical geography, which obviously studies the natural landscapes. And in particular, we will be looking at the UK's physical landscapes. Now, the physical landscapes in the UK have been shaped mainly by geology, tectonics, glaciation, and human activity. So moving on to rock types, it will be important for us to identify the three main rock types that will be discussed in this particular topic. And as you may have obviously studied these at Key Stage 3, we know that the three main rock types are igneous, sedimentary, and metamorphic rocks. Now, it will be important for our examination to be able to identify the characteristics of each of these different types of rock. So for igneous rocks, these are obviously the oldest and the most resistant rocks, and they are formed from tectonic or volcanic activity. So when lava cools down, obviously it will form igneous rocks. And examples here are granite and basalts. Then moving on to sedimentary rocks, these ones are the least resistant, and as the name suggests, sedimentary rocks, these ones are formed as sediment is deposited by rivers or the sea. Now, that sediment will build up in layers over time, and the upper layers are likely to compress the lower layers, and that will form rocks. Now, in a lot of cases, fossils, obviously, that have dropped down to the bottom of the ocean, for example, are going to be trapped in between the layers, and this will help in the sedimentation process of these rocks. Not the sedimentation process actually, but the cementation process. So they will tend to hold these layers or particles or sediments together. And obviously over time, yes, this builds sedimentary rocks. And these are the least resistant types of rock. Examples here obviously are clay, chalk, sandstone, carboniferous limestone, and millstone grit. You could pause the video here and have a look at the features of these sedimentary rocks in detail if you like. And moving on to the next one, next type of rock, the metamorphic rocks are formed as a result of extreme heat and pressure. For example, sandstone, which is a sedimentary rock, becomes quartzite when exposed to extreme levels of heat and pressure. And you have the examples again on this slide. So slate, schist, and marble. So what does the rock type then have to do with the physical landscapes of the UK? Now, generally speaking, the type of rock will influence the relief or the topography of the UK. Now, relief or topography refers to the height of the land, and the types of rock that we have will determine where we have upland landscapes and where we have lowland landscapes. And as a general rule, the igneous and metamorphic rocks will erode slower because they are more resistant and will end up forming upland landscapes. Then the weaker sedimentary rocks will erode faster to form lowland landscapes. Although having said that, some of the sedimentary rocks are slightly more resistant and may end up forming upland landscapes, as we'll find out later on. So this map here shows the distribution of different rock types across the UK. And as you can see from the map, if we look at this area here to the south and the east, southeast of the UK, we mostly have the sedimentary rock. Now, obviously, these are the least resistant rocks, and these areas here to the south and southeast of the UK are lowland landscape. Then the areas to the north and the west of the UK mostly have igneous and metamorphic rock, and that igneous and metamorphic rock obviously is eroding a lot slower and forming upland areas. So that brings us next to the Tees-Exe line, which is this line along here. Now this is an imaginary line, just like the equator, the Tropic of Capricorn and Tropic of Cancer. So they're all imaginary lines, but this is not necessarily a line of latitude like the other examples that I've given. But this here is an imaginary line that runs from the River Tees to the River Exe. And this line actually divides the UK into upland landscapes to the northwest and the north, and then lowland landscapes to the south and the southeast. So this slide here shows the geology map and the relief map side by side. The intention of putting this here is to determine the relationship between geology and relief here in the UK. And obviously, as we can see again, to the northwest and north of the Tees-Exe line, we have the upland landscapes. So here it's represented by the brown areas of land that obviously have got the higher relief, and it's in those same areas that we have the metamorphic and the igneous rocks. And then to the southeast and south of the Tees-Exe line, we have the lower relief, mostly in green and a lighter shade of brown, and it's those areas that have the sedimentary rocks which are less resistant. So there is actually a direct correlation between the relief and the geology of the UK. Now this here is the type of graphic that you're likely to find in an examination question, where you may be asked to assess the influence of geology on the relief of the UK, for example. So this is an important one to remember here. So this slide here shows a picture of Malham Cove, which is an upland landscape in the Yorkshire Pennines. Now this was once a very huge waterfall here in the UK, and as you can see from the picture, it's quite high. So at 80 meters high, which is 30 meters higher than Niagara Falls. Now it's mainly formed from limestone, and it contains shells of corals that lived in tropical seas over 300 million years ago. So the question is, how did it end up 300 meters above sea level right now, when it was originally beneath the sea or beneath the oceans? So one of the explanations here that we can give for why we have an upland landscape that was once under the sea is that the UK was once covered by tropical seas. That was around 300 million years ago, and that period is normally referred to as the Carboniferous period. So it was almost like the Great Barrier Reef of Australia. And as the fish died that lived in the seas, they obviously fell to the ocean floor, and together with the deposited sediment, they formed horizontal layers of sedimentary rock, and which obviously is referred to as Carboniferous limestone. So the layers, however, will vary in hardness, and the most resistant of these layers is the Millstone grit, which forms the highest peaks in the Pennines and will protect the sands and the shells beneath. Now, as you can see here in this cross section here that is on the slide, the Millstone grit is the one right at the top here, and that obviously is the most resistant. And then we go on to the shells and the sands below, and those ones are less resistant and have eroded faster. Okay, now we will come on to explain why the rest of this particular cross section looks the way it is as we go along. But as you can see, there's this line here that is going across that shows the height of the valley before the Ice Age. And so it looks like the Ice Age did make a lot of changes, and we'll see that as we go along. So the rocks in the Pennines have been affected by three main tectonic processes. The first one is continental drift. Now we know that that theory of continental drift suggests that continents tend to drift away from each other or towards each other because of convection currents that are acting underneath them or at work beneath them. So the continental drift meant that the plate on which the UK sits moved away from the tropics and ended up in the mid latitudes where we are at around 58 to 60 degrees north of the equator. And then the second process, tectonic process, was uplift. So we know that as plates move as well, they can tend to be pushed upwards, and this is what happened in this case. And the carboniferous limestone rock that was below the sea was pushed upwards to form land. So instead of it being under the sea, it was pushed upwards and is now above the sea level. And then thirdly, faulting also took place, which is another tectonic process. And some of the rocks snapped as the uplift was taking place. And this formed steep edges, which are known as fault scarps. Now, Gigglewick's car in the picture here is an example of that faulting that led to those fault scarps. And as you can see here, there's a very, very steep scarp slope right here that drops down right to the bottom of this particular valley here. So this here is an example of the faulting that took place. So three tectonic processes: continental drift, uplift, and faulting. So as the Pennines were uplifted, drainage basins were created. Now, on every kind of upland landscape that you have, you're likely to have a drainage basin, which is draining water from the landscape around it. And especially because it's an upland landscape, there's the force and the pull of gravity, obviously, that is causing the water to flow down, the landscape towards what you can see here as in the form of a V-shaped valley. Now, the water obviously is flowing either through surface runoff, through flow, groundwater flow, and so on, and ending up in the bottom of this river valley here, which is in a V shape. However, this kind of shape of a river valley was then changed and transformed by glaciation, which is a process that took place here in the UK around 10,000 years ago. Now, we know that the Earth experiences glacial periods as well as interglacial periods. So the interglacials are the warmer periods, and then the glacial periods are the colder periods, where we have a lot of ice sheets that are moving across the landscape. And that is what happened here in the UK around 10,000 years ago. And these V-shaped valleys, due to the ice age, were then deepened and widened. And that eventually formed this U-shaped valley that you can see in this other picture here. And you can also see that again on this cross section here of the Wharfdale, in the Pennines. So glaciation also had a big role to play in the shaping of the landscape of the Pennines because it transformed or changed V-shaped valleys into U-shaped valleys. Now that brings us to the conclusion of this particular video. In the next one, we shall be looking at the two case studies of upland landscapes, one for upland landscapes in the UK and the other one for lowland landscapes here in the UK. Thank you. Bye-bye. Okay, so the example of an upland landscape that we are going to look at is the Lake District here in the UK. And there are physical processes that are taking place here, and we are going to divide them into two categories. Now, the first category we are going to look at is weathering and slope processes. So weathering is the breakdown of rock, and in this case here, freeze-thaw weathering is the type of weathering that is taking place. Now, there are variations in day and night temperatures. And because of those variations, we end up with water during the day when the temperatures are above freezing. Water goes into the cracks that are in the rock. Then at night, when the temperatures drop below freezing, so below zero, that water turns to ice. Now, ice will take up 10% more space than the water, and because of that, the cracks that are in the rock are going to widen, and that rock is eventually going to break up. Now, when it breaks up, the fragments that are the result of this process are called scree, and scree is what you will find on the valley slopes in the lake and in a lot of parts of the Lake District. So on top of this, we also have slope processes that will now take place and affect those valley sides. And one of the processes is rock falls. Now we know that the rocks can be quite unstable, like the ones you can see here. All of them are different shapes and sizes, and therefore they will not sit on top of each other, in a way that does, that where they would not move, for example. So because of that instability, the rocks are likely to move down the slopes due to the pull of gravity. And then the second slope process are landslides, and these ones occur during periods of heavy rainfall, and that causes the rocks that are on the slopes to get heavier and therefore slide down the slopes. Now, the second category that we said that we'll look at here is postglacial river processes. Now, postglacial obviously here is referring to the time after the last ice age here in the UK. And now that last ice age here in the UK took place around 11,000 years ago. And at that time, the Lake District experienced glaciation, which refers to rivers of ice that are flowing down the landscape. So this led to the formation of U-shaped valleys that now have misfit rivers. Now, what that means is that we previously obviously had river valleys which are ordinarily V-shaped, but because the ice will do a lot more erosion, those V-shaped valley sides were converted or changed by the erosion that is caused by the glaciers into U-shaped valleys. Now, because they are very, very wide, and we now have rivers flowing at the bottom of them, the rivers sort of look misplaced, and that's why they are called misfit rivers. Now, during times of heavy rainfall, sometimes these rivers will burst their banks, and when they burst their banks, they will deposit alluvium in the valley bottoms, and that makes these places here in the Lake District really good for farming, because that alluvium, or that silt, if you like, forms, is rich in nutrients and therefore forms good soils for farming. So the example of a lowland landscape that we are going to be looking at is the Weald here in the UK. And we are going to be dividing the physical processes that take place in the Weald into two categories. So we have the weathering and the slope processes. And the cross section above shows how the rock strata in the Weald was continuous, forming an anticline. So you can see here where you have the kind of perforated line is where the anticline used to be, or where, where the anticline used to be. But over time, erosion has left alternate layers or alternate strata of more and less resistant rock to leave scarps and veils. So you can see where the erosion has taken place here, and then you have, as a result of that, and then over here as well, and then as a result of that, you have the scarps over here and the veils, which are the valley bottoms. So the scarps will be the steep hillsides, which you can see here, and then the veils will be at the bottom over here. Now, the main type of weathering that is taking place here is chemical weathering, and that happens when chalk, which is one of the layers of rocks here, dissolves into acidic rainwater. So obviously some of the rain may contain little amounts of acid, and that obviously dissolves some of the rocks such as the chalk. And that will happen because there are warmer temperatures in the south of the UK. And then we also have biological weathering taking place because, as you can see here, we do have vegetation on the landscape. So that means that when the roots of these plants here go into the cracks in the rocks in this particular area, and then as the plant grows, those roots are going to get bigger. And as they get bigger, they are going to expand the cracks in those rocks and cause those rocks to break up. So coming on to or getting onto the post-glacial river and slope processes here, we know that chalk is a permeable and porous rock, and therefore, after the ice here had melted, the water that was a result of that then infiltrated into the soil, and that has led to dry valleys in the Weald. And the main slope process that is taking place over here is actually soil creep, and that's because the valley sides here are a lot more gently sloping than the ones that you'd get in the in the Lake District. So that means that when you get very heavy rainfall, materials, the unconsolidated material is likely to flow down the slopes at a much slower rate, and that's why it's referred to as soil creep. So having looked at the physical processes that take place in different landscapes in the UK, so upland landscape and lowland landscapes, we are now going to look at the impact of humans on the landscape. And this is obviously in the form of human activity. And the first one we'll look at is settlement. Now, the population of the UK keeps growing, and as that happens, people will need houses to live in. And urbanization is also likely to take place. And as more and more houses are built, then the landscape is going to change because it's going to be built on and therefore will look different. Then we also have farming. So again, the population is growing, there's demand for food, and this has led to a lot more land being taken up for farming. Now, originally, or in the past, the landscape used to have hedgerows because there wasn't as much heavy machinery being used to farm the land. Most of the work was done by hand, and therefore there were hedgerows to sort of demarcate or put boundaries between different areas that were being farmed. But with the introduction of mechanization, where you have to use bigger machinery, obviously either to plow the land or spray the crops or harvest the crops using combine harvesters and so on, a lot of those hedgerows had to be gotten rid of to make way for the big machinery. And that again has changed the landscape. So from a landscape that had hedgerows to one now that has got very big open fields where intensive farming is taking place. So the landscape is continuously changing. And then we also have hill sheep farming, which is going to be taking place in the upland landscapes. And then arable farming, which is the growing of crops, is likely to be taking place in the lowland landscapes, also creating distinctive landscapes and changing the way the landscapes look over time. So the last one we look at here is deforestation and afforestation. And deforestation, obviously, like you know, is the cutting down of trees. And we need the trees for wood, for example. And so the deciduous woodland is what originally was here in the UK, but a lot of that has been felled over time, as in it has been cut down. So for timber, for paper, and so on. And some of it has been replaced by coniferous trees, which are slightly different. They're like, they are cone shaped, like the Christmas trees. And so in the UK, the landscape has changed in terms of the vegetation that you have. So from deciduous woodland to coniferous woodland in some places, and then in some places a mixture of both where you have mixed woodland. And all this that is happening is creating distinct landscapes or landscapes that are changing and evolving over time. So coasts have a large role to play in shaping UK's physical landscapes. And the first thing that we look at in relation to coasts is how climate and erosional processes affect coastal landscapes. So erosion is the wearing of the land by either water, wind, or ice. But in this case, when we are talking about coasts, we are talking about how the coast or the land is being affected by wave action or being worn away by wave action. And when talking about waves, waves are created or caused by the friction that results from wind blowing over the surface of the water. Now, that friction is what creates small ripples, which eventually turn into waves. And the stronger the wind and the longer it has blown for, then the bigger the wave is going to be. So the distance that the wind has blown over is normally referred to as the fetch. And obviously, the longer the fetch, then the bigger the wave. And in the UK, the strongest winds are in the winter. And those winter winds normally cause destructive waves. And then constructive waves are in the summer when the winds are not blowing as strong. So destructive waves then. So these occur in the winter and are referred to as plunging waves. They are a lot taller and they will crash onto the beach. As you can see here, the wave height is actually fairly high compared to the wave height here for the summer waves, which are the constructive waves. So because of this height here, when they get onto the coastline and as the water becomes a lot more shallow as it approaches the coast, it makes the wave even bigger. So when the waves get onto the land, they are fairly high, and then they crash here onto the sand or onto the beach. And when that happens, they loosen that beach material. So that movement of water onto the beach here and crashing down on it is called the swash. And then the backwash is when the water now washes back into the sea or the ocean, if you like. And when this material here that has been loosened is moving back, when the material is going to be loosened, and then it's going to be dragged back into the sea. Now, when that happens, the beach is going to lose material or lose the sand that is on the beach. And that's why we refer to this here as a destructive wave, because it's destroying the beach. And the problem with this is that the beach is the first line of defense, is the basic protection for the coastlines, because it's the beach or the sand that is on the beach that will break the wave or slow down the wave before it gets to the land. And therefore, the less of a beach you have, the more that coast is likely to be eroded by future waves. Okay, then moving on to constructive waves. These ones here have a stronger swash than backwash. And because of that, they are likely to form a wide and gently sloping beach, which is better in terms of slowing down the rates of erosion. Now, because the swash is stronger, it's going to wash up material onto the beach. And then because it's weaker as it comes back, it means that some of the water will get time to infiltrate the sand, and that as that happens, the material it was carrying is going to be dropped or deposited onto the beach, therefore creating a wider and more sandy beach. So how does geological structure and rock type influence coastal landforms? So geological structure here is referring to the way the layers of rock are laid out along the coastline, and then the rock type will be referring here to the types of rock, whether they are sedimentary, igneous, or metamorphic. And then within sedimentary rocks, we also have different types of rock, such as limestone, clay, and chalk. And we know that all of them have got variations in terms of how easily they are eroded. So that is going to affect the way the coastal landforms are going, where different types of coastal landforms are going to be found along a coastline. So we have two different types of coasts, and the first one we are going to look at here is discordant coastlines. So at a discordant coastline, the rock layers, as you can see here, are laid out perpendicular to the coastline or to the sea. So if this is a sea here, this is a sea here, and you can see that the rocks are perpendicular to the sea or at a right angle. Now, when this happens and you have variations in the rock strata and the rock type, then that is likely to lead to different rates of erosion. So, for example, we have this middle layer here, which is clay and sands. Now, these ones here are quite unconsolidated. It's unconsolidated material, not as consolidated as the other two. So this one here is going to be softer and a lot easier to erode. And as you can see, that has eroded faster here to form a bay. And then the other rocks here, which is limestone up here, and then chalk, which are both harder, have been left as outcrops or sticking out to the sea, and they form what are called headlands. So you have Ballard Point here, which is a headland, and then you have Dalston Head here, which is also a headland. Now this obviously is in Swanage in the Dorset coastline. So you have, so I've explained that. So, and then you have concordant coastlines. Now the way to remember these actually, if you have discordant, it means that they are up, the way I would remember this is, say disadvantages. So disadvantage, discordant, disadvantage, discordant. So that means it goes against. So it's not flowing. This rock strata here is not flowing in line with the coast. Instead, it's perpendicular to the coast or at right angles. But then when you get to concordant coastlines, those ones are running parallel, as you can see here, to the coastline, because the sea is here and the rocks are running parallel over here, as you can see, and therefore these ones are in line with the coastline, hence the name concordant coastline. Again, here we have different geological structure. We have different types of rock here, and if the rock that you have on the outside here or nearest to the sea is fairly resistant, it will erode a lot slower, right? But it will still erode. Now, after it has eroded through the harder strata of rock, then it will get to the softer rock behind it, and that will be eroded a lot faster, as you can see is what has happened here. And then behind it, the next layer there is going to be a lot more resilient and a lot more resistant, and as a result, the erosion is going to slow down. And when it slows down, at the back here, you're going to have cliffs forming, but then here where you had less consolidated material or softer rock, you will end up with a cove forming. And our example here obviously is Lalworth Cove, okay, here in the UK. So there are 4 different types of erosion that take place along the coastline, and I think it's worth a mention here very quickly. And the first one we are going to be talking about here is hydraulic action. Now, hydraulic action involves the force of the water forcing its way into cracks in the rock. And when that happens, it causes compression of air within the rock. And then as that wave retreats or moves back, that compressed air will blast out of the rock, and that is likely to cause that rock to disintegrate. So hydraulic action is the shear force of the water forcing its way into cracks in rocks and causing them to break up or to disintegrate. Then we have abrasion, and this occurs when the rock that is, the rock and sediment that is being carried by the waves scrapes against the cliffs and causes them to wear away. Then we have attrition, and attrition is where the rocks that are being carried off that are being carried by the waves and that have been broken up from the cliff will knock against each other, and as that happens, they are going to break down into smaller particles. Then lastly, we have solution, and this is where some of the rocks that are soluble in water are going to dissolve in the water. So we talked about discordant coastlines where the rock strata is perpendicular to the coastline or perpendicular to the sea. And I'd like us to look at what happens on the headlands that are formed there. So we said that where we have soft rock, you're likely to end up with a bay because that soft rock is going to erode faster. And in that bay, you're likely to have the formation of a beach taking place because material is likely to be deposited there. That particular bay is going to be sheltered from the waves on either side by the headland outcrops that will be on either side, and as a result you'll have the formation of a beach. But then on the headland, what is likely to happen there? That's what we are looking at on this particular slide and on this diagram here. So the process starts off with a crack in the headland. As you can see, this is a good example of a crack in the headland. And with time, we said that you have hydraulic action taking place due to the waves, and as those waves attack that crack there in the headland, the shear force of the water and the hydraulic action is going to cause that crack to continue widening, and as it widens, it's going to form a small cave. Then over time, that small cave will continue to erode to form an even larger cave. And then eventually, as the erosion continues to take place through hydraulic action and abrasion, that cave is going to erode all the way through to the other side of the headland. And that is going to leave an arch like you can see here. So this here is an open arch here. And over time, the arch also the roof of the arch is likely to collapse. And the reason why it's likely to collapse is because you also have subaerial processes that are taking place on top of this arch here. So you could have chemical weathering, for example, taking place up here and weakening the rock further. And then because you also have that pull of gravity, this top part here is going to be compromised and will eventually collapse. Now, when it collapses, what you end up then is a stack. So this is your stack here that has remained after the roof of the arch, which was somewhere here, has collapsed. Okay, so that's a stack there. And then the stack again is being attacked at the bottom here again by the hydraulic action, the abrasion that is being caused by the waves, and eventually it will also break down and will end up as a stump. Okay, so this is what happens at a headland, and you get caves, arches, stacks and stumps on a headland, and those are coastal landforms. So longshore drift is a process that will happen along coastlines, and this is a very important one to talk about. And it's the movement of sediment along a coastline in line with the direction of the prevailing wind. Okay, now if we look at this particular coastline here, obviously we have the sea in blue, and then we have the beach here in a light brown color. And this here, as you can see, the white arrows here represent the prevailing wind direction. So the wind is blowing from the southeast in this particular picture here, and as that happens, it's going to bring waves, and those waves are going to bring material up the beach. So the material or the sediment is being represented here by this pebble here, and it's going to bring the material up in line with the direction of the prevailing wind, as you can see. So it's at an angle. And then that is a swash, and then the backwash will be perpendicular to the coastline at a right angle, as you can see here. And then again, that pebble will be moved up in the angle, in line with the angle of the prevailing wind. And then again, down, the backwash is going to be at a right angle, and that process is going to keep on repeating itself. And as that process repeats itself, it means that material and sediment is going to be moved along that particular coastline in line with the direction of the prevailing wind. So the waves do three main jobs actually. They erode material, then they transport that material, and then they deposit that material. So they do those three jobs, and in so doing, they create different landforms. So the landforms that we had talked about previously were bays. So those ones are depositional as a result of erosion, first of all, and then deposition that has taken place. And then we talked about the headland as well, And at the headland, those are erosional landforms that are created at the headland, and we talked about caves, arches, stacks, and stumps. Okay, but now we are going to be looking at depositional landforms, and these normally form when the waves have lost their energy and therefore they don't have a lot of power to continue carrying the sediment, and as a result of that, the sediment is going to be dropped due to that low energy, and that dropping of the sediment is what we are calling deposition. And the deposition is likely to form spits, hooks, and salt marshes. Now, in this particular case here, we have a spit being formed here, right? So this extension of sand here out into the open water is what we are calling a spit. So what happens is you have longshore drift taking place here. Again, we said longshore drift is movement of sediment along a coastline in line with the direction of the prevailing wind. And you can see the prevailing winds here are approaching from a southwesterly direction. So the sand is being moved, or sediment is moved along this coastline in this direction. But then there's a change in the coastline here, right? And because of that, the coast has curved the other way to this side here. However, if we have shallow and calmer waters out here, this sand that was being deposited by the longshore drift process is going to continue being deposited out into that shallow, calm water, and that is where the spit is going to be formed. So a spit is an extension of the land, really, due to the process of due to that longshore drift process. Now, sometimes there will be a change in the direction of the wind, and if there is a change in the direction of the wind, then you will have this spit here curving at the end, and you can see here you have curves here of the spit, and that is normally referred to as a recurved end or a hook, all right, on the spit. Now, behind the spit over here, you're likely to have the development of salt marshes. And that is because you will have a lot of material being deposited here. Now, the reason for that is that this particular part here of the water has very low energy because it's sheltered by the spit on this side and sheltered by the coastline on this side, and therefore, and if you look here, this is the direction of the prevailing wind, so it's really not being reached by the waves as much. And because of that, you will have deposition of material here due to that low energy, and that is likely to form those salt marshes that we are talking about. And salt marshes tend to be very good habitat for rare species of birds, for example, on the coastline. Okay, so a few more depositional landforms to talk about here. So we have bars, lagoons, tombolos, and sand dunes. So if starting with the bar, so here you have longshore drift taking place, and if you have a small bay, sometimes that longshore drift is likely to carry on right across that particular bay, and when that happens, the bay will be blocked off. And because of that, you will this particular landform that is created here that is blocking the bay is referred to as a bar. And then behind the bar, you will have a lagoon forming, again, which is likely to be a very low energy environment. And because of that, you're also likely to have the formation of salt marshes and so on, which again will provide a good habitat or a great habitat for rare species of birds. Then we have tombolos, and those ones are formed when a spit connects a mainland, like this one you have here, with an island that is out there. So you can see there is a connection there, and that is what is referred to as a tombolo. Then lastly, we have sand dunes, and these ones here will form when sand is blown further inland by the wind, by the wind. So the sand is being blown in by the wind further inland, and that will form sand dunes. And over time, you're likely to have vegetation beginning to grow on those sand dunes, and that will cause the sand dunes to become a lot more, a lot firmer. and therefore continue to spread out a little more inland. So how has human activity influenced coastal landscapes, or how has it changed coastal landscapes? So again, we are going to start off with settlement as the first human activity. And we know obviously that the population of the UK continues to rise. And as a result, there's a higher demand for housing. And as that happens, we end up with housing being very expensive in the urban cores. Now, because of that, people then look for other places where they can settle down. And one of the the more attractive places or propositions to be is the coastline. And you end up with a lot of retirement migration of people who lived previously in the urban cores looking to buy cheaper properties out along the coastline. And you also have, for the coastlines that are closer to the urban cores, you have commuters who live there and then work in the urban cores. So that obviously causes a lot of building of houses and the infrastructure that is needed or required to support that housing. And as a result of that, you end up with the coastal landscape changing quite a bit. Then the second human activity here is farming. Now, with an increasing population means an increasing demand for food. And if there's an increasing demand for food, it means that some farms are likely to be found near coastal areas. And that obviously is going to take up the land that is at the coast and make it look different, and also put pressure on wildlife habitats that are along that particular coastline. Then we have industrial and commercial land use as well. So some of the coastlines are being used, as gas terminals, oil refineries, and for power stations as well. So, for example, where you'd have tidal power, being done, or even wind farms. So, those types of land use are likely to change the way the coastline looks. Then you have the land also being used for tourists, for tourist recreation, for shops for the tourists, and also as office space. And all that obviously is changing the way the coastlines look. Then we also have coastal management. So because of that coastal erosion that we've been talking about, some of the coastlines need to be managed, or they need to be defended against the erosion that is taking place there. So you have to put up either hard engineering in the form of seawalls, groins, and rock armor or riprap, and then you also have soft engineering as well. And all that, or all those structures, are likely to cause a difference in the way that coastal landscape is going to look like. So human activity is also leading to climate change. So we are now going to look at climate change and cliff processes on coastal landscapes. Now, the erosion along the coastline is likely to continue to rise due to climate change. And global warming is likely to cause, ice caps obviously to melt, which is going to lead to rising sea levels. And rising sea levels will mean that we are going to have bigger storms, we're going to have bigger waves, which obviously cause a lot more erosion and is likely to lead to flooding of low-lying areas. Now, we also have thermal expansion, which is likely to be a problem because as the temperatures rise, the seawater is likely to expand as a result, and that obviously is also likely to lead to bigger storms. So the first type of cliff process that we'll talk about here is cliff erosion. Now we have a diagram here showing a cliff face, and initially what will happen is that the bottom of the cliff face is going to be attacked by the waves, and those waves obviously have hydraulic power, and if there is a crack on the cliff face, that hydraulic power or hydraulic action is going to act on that particular cliff face, and over time a wave cut notch is going to form. Now as that happens, this top part here of the cliff is going to be undercut because it will not have any material that is below it to support it, and over time that is likely, or that particular undercut area is likely to collapse here into the sea. And as that happens, the cliff face is going to keep retreating back as the process continues to repeat itself. So this particular cliff here is being eroded, and that is what we are referring to as cliff erosion taking place. And it's worth a mention here that whatever is going to be left here is what is referred to as a wave cut platform, because obviously the waves have continued to act on this area here to leave that platform behind here. And then the second cliff process that we are going to talk about is cliff slumping and rotational slips. Now this here is an example of mass movement of sediment and material at the coast. And it happens when you have a more permeable layer of rock sitting above a more impermeable layer. And that will mean that during times of very heavy rain, the rain will soak through the more permeable layer a lot faster. And as it soaks through, it will then get to the impermeable layer below it. And when that happens, that impermeable layer is going to cause the water to sit right above it. And as the water sits above it, the rock above, well, the material above it is going to be saturated, obviously. And that saturation is likely to cause the rock to become very heavy, and that rock is then going to, or the material is going to slide off that particular cliff face, as you can see is happening here. And that process is what we are calling rotational slips. And those are causing the material that is on this cliff, for example, to be washed out into the sea. So the next thing that we're going to look at is coastal management, and we'll look at the traditional approaches that were used or have been used in the past and up to now as well to protect coastlines. Now, coastal management obviously refers to the way coastlines are defended against coastal erosion. And before a decision is made as to what coastal management is to be put in place, or whether it should be put into place or not, a cost-benefit analysis is going to have to be done. And that cost-benefit analysis is going to determine whether that particular section of coastline is worth protecting or not. So if the area has a lot of value, so for example, we talked about, say, gas terminals along the coastline. So those obviously are going to be very valuable. They are making money, and then they also have cost a lot to put up. So if the cost of them is a lot higher than what it would cost to defend that particular coastline, then you will want to defend it because that infrastructure is valuable and it is costly. So your cost there for defending the coastline will be a lot less than the benefit that you're getting from actually defending the coastline. Okay, so when you're defending or managing the coastline, you're using either hard engineering or soft engineering. And in this particular slide here, we are looking at three types of hard engineering. And the first one here is a picture of a seawall. And this seawall, as you can see, is a recurved seawall. So it curves upwards over here, it curves in over here, and then upwards, outwards here. And that is so that it can reflect the waves back into the ocean. Now, by doing that, it's obviously defending the land that is behind it here. And it's a very effective defense against coastal erosion. Now, when we are talking about sea defenses, we also talk about the cost and the benefit or advantages or disadvantages of them. And the main advantage is that this one here is very effective, or the seawalls are very effective. But the limitation is that they are very expensive. And apart from the expense, they don't necessarily look very natural and therefore spoil the look of the landscape. Some people may argue that, they prevent access to the beach. You can't go directly to the beach. You've got to go down steps and so on. So there are obviously advantages and disadvantages. So the next one that we are looking at here are groins. So you can see that these stretch out into the water here. And the idea behind this is to trap sediment. So we talked about the process of longshore drift earlier. So the movement of sand along the beach. And if that is happening and sand is being depleted from a particular beach, especially if it has valuable land behind it, then it means that that basic protection in the form of a beach is removed by longshore drift. So you want to protect that particular coastline from that longshore drift, and you want to accumulate the sand using those groins so that the sand can act as your first line of defense. And that's what these groins are doing here. Now, again, they also have advantages and limitations. And obviously, one of the limitations, as you can see, is that they look unnatural. They're not very natural here. And then if you have tourists that want to enjoy this beach here, they may be hindered by these groins here. If you have, say, people who want to jog along the beach, they are, they're to some extent preventing that. Okay, but again, they're effective in defending that particular coastline, and that's an advantage of them. Then lastly, here we have rock armor or riprap, and these here are large boulders or rocks that have been placed here along this particular cliff face here, and these here will dissipate or absorb the power of the waves, and by doing that they are defending the cliff that is right behind them here. Now, it could be argued that these look a lot more natural than the two above here. However, they can be also quite costly, which is a limitation. So we are now going to look at the modern approach to coastal management. And one of the things that we actually did not mention with the groins, for example, is that sometimes, well, the groins can cause what is referred to as the terminal groin syndrome. Now, that basically means that you may end up with material and sand being trapped on one particular section of the coastline, and then places that are further along that particular coastline are likely to be starved of sediment and material. And because of that, those places further down along the coastline are going to have faster rates of erosion as a result of protection somewhere else on that particular section of coastline. So that calls for a more holistic approach to the way a coastline is being managed or defended. And that means that the entire coastline is taken into consideration. So not just an isolated section. You're thinking about the coast in its entirety. And this approach is referred to as the Integrated Coastal Zone Management, or ICZM. And plans called shoreline management plans, or SMPs, are drawn up for long stretches of coastline. Now, there are 4 choices that UK councils can make in terms of what approach to take in defending a particular coastline or managing it. And one of those is to hold the line. And holding the line refers to the use of sea defenses to prevent coastal erosion and maintain the coast at its current position. So you're just holding the line, you're maintaining that coastline where it is, you're defending it against the waves. Okay, so obviously the strategies that we have looked at under this include hard engineering, which obviously is rock armor, you have the sea walls, and you have the groins as well, and that can be costly. So the second choice on defending that can be, the management plans can opt for, is advance the line. So that basically means that you're using sea defenses to advance that particular coastline out further into the sea. Now, obviously, that is likely to be very expensive. Okay, so that is a limitation of it. And then the third option here, or the third choice, is strategic realignment or strategic retreat. So this involves allowing the coast to retreat slowly and gradually as people are relocated from that particular area or from the areas that are at risk from erosion. And then the last one, obviously, is to do nothing and let nature take its course. But this will be mostly in those areas that where a cost benefit analysis has been done, and the benefit of protecting it is outweighed by the cost. So the area is not likely to be as valuable, and therefore it's not worth protecting. So we'll now move on to soft engineering as a form of coastal management. And this will involve normally the use of natural processes to protect coastlines. And the first one we're going to look at here is cliff stabilization. So here you're basically trying to make sure that the cliff face does not experience rotational slips, or what we call slumping. So how do you do that then? So if you look at this particular cliff here, you have drains that have been put in, and these drains are obviously taking out the excess water that is sinking down, or that is infiltrating this softer layer of or more permeable layer of rock above here. So that will prevent saturation of that particular cliff face, and obviously will prevent those rotational slips. Okay. And then we have planting vegetation as well. And as you can see, this particular cliff face here has some vegetation on it, and that vegetation is going to hold the material together through the roots of the vegetation, and that obviously is going to prevent the slope processes from taking place. Okay, so the material from being washed down the slope over here by the force of gravity, and especially during the times of heavy rainfall. Then we have offshore breakwaters, which you can see out here. So this here will involve the building of walls of rock armor that are offshore. And these will reduce wave action along that particular coastline, because as you can see here, you have an accumulation of material right here. But if this offshore breakwater was not here, this sand here would not have accumulated, and the entire area here would be a lot more susceptible to coastal erosion. Then we have beach replenishment, which is the last one we are going to look at here. And as you can see here, we are basically just adding sand onto the coastline, and we said that the sand or the beach is our first line of defense, and the beach obviously is absorbing the power of the waves. So we are now going to move on to rivers, and rivers obviously as well have a big role to play in shaping the landscape of the UK. Now, on its journey from source to mouth, a river will flow through three main courses. So you have the first one here, which is the upper course of the river. And as you can see here, this is referring to the highland areas that are near the source, so where this river begins. And then it will flow on to the middle course, which is less steep, and then eventually to the lower course, where the relief is a lot lower and almost flat, really, as you near the mouth of the river. So while this river is moving, it will do three main jobs. It's going to erode material, it's going to transport that material, and then it's also going to deposit that material. And those processes that are taking place there, that erosion, transportation, and deposition, is going to lead to the creation of various landforms. And again, here the types of erosion are similar to the ones that we talked about when we are studying coasts, and those are hydraulic action, abrasion, attrition, and solution. So we have types of transportation. So the river has eroded material. Now that material is then going to be moved. And the first way in which material is moved is traction. And traction refers to larger rocks, the way larger rocks are moved along the riverbed. Now, because they are heavy, they are going to be on the riverbed, and as the river flows along, the river water is likely to roll those boulders or large rocks along. So the flow of the water is, causing them to roll along the riverbed here. Then we have saltation, which is the second type of transportation, and that is where smaller pebbles, so these ones down here, will bounce off the riverbed and keep moving along that particular course of that river. And we call that a leapfrog motion because you can see it's almost jumping up here and then hitting the bottom again, and then that force is causing it to rise again and then drops, and then it keeps bouncing along. So that process is called saltation. Then we also have material that is being carried in suspension. So as you can see here, these here are a smaller sediment in comparison to the boulders and the pebbles, and these are the finer material that can be carried along in the flow of the water. It's light enough to be carried in a suspended state in the water, and this actually is the material that normally causes the water to look very discolored during times of very heavy rainfall, because during such times the river has a lot more energy and is likely to be carrying a lot more material that it has eroded. So that will be carried in suspension. And then lastly, we have solution, and this is where again weak acids in the rainwater are going to cause some of the material or the rocks to be dissolved and carried along in a solution or a dissolved state. Okay, so what landforms occur in the upper course of a river? The first one that we are going to be talking about is waterfalls. So the formation of a waterfall here is what we are looking at. And in the upper course of a river, you will have areas that have two different bands of rock. One band that is hard rock above, as you can see here. This here represents a hard rock. And then you have softer rock below here. Now, as this water is flowing through this section here, it's going to drop down here. And because this area here has got softer rock, that rock is likely to be eroded a lot faster than the rock that is above it here. Now, as you can see over time, that erosion of this rock here is going to cause a big plunge pool or a huge plunge pool here. It's called to be formed, right? And then this top rock here, which is a hard rock, is going to be undercut. So there will be no longer any material that is holding it up here or helping support it up. That material will have been washed off, and eventually, because of that undercutting, the force of gravity is going to cause it to fall through or to fall down. And then it's going to come down here into the plunge pool. It's likely to cause abrasion to take place as it scrapes, on the bottom here. And then as the attrition is taking place as well, the particles, the rocks are hitting against each other, the ones that broke from here, becoming smaller and so on. And this process will continue to repeat itself. And as that process repeats itself, this waterfall is going to keep receding. It's going to retreat or to recede or to move back. And as that happens, you can see this here, this dashed line here represents the former location of that particular waterfall, which has now receded all the way over here. And this area here, where it receded from, or where it used to be before rather, is referred to as a gorge. Okay, so waterfalls rather are a landform that is created in the upper course of a river. Then we also have V-shaped valleys. So the river water at this stage here does not have as much energy, but the energy that it has will be used for vertical erosion. So it's going to be eroding downwards, and because of that downwards erosion, you're going to end up with a V-shaped valley, okay, as you can see up here. But then because the river doesn't have as much energy, it's going to be trying to find the path of least resistance to move along. And as that happens, it's likely to bend and curve as it does that. And because it's doing that, as it moves across a landscape, we don't then see a V-shaped valley that is straight. Okay, we can see that it's interlocking. We have interlocking spurs here, right? As the river is bending, you have interlocking spurs here. That is what we are referring to as interlocking spurs as it bends around the landscape and tries to find the path of least resistance. So three landforms that are formed in the upper course: waterfall, V-shaped valleys, and interlocking spurs. So in the upper course of a river, we will have weathering and mass movement taking place. Now, the three types of weathering here will include all of them, really. So we have freeze-thaw weathering, which obviously is where the water enters the rocks, the cracks that are in the rock during the day, then freezes at night. And when that happens, the rock then eventually will break up into smaller pieces, and that unconsolidated material, or those fragments rather, are referred to as scree. And then we have biological weathering taking place as well. You have the vegetation that is here as the roots go into the cracks that are in the rock. And as that particular plant grows bigger, the roots grow bigger as well, and they cause that particular crack to become bigger, and eventually the rock breaks up. Then we have chemical weathering, which is where the acid that is in the rainwater will dissolve some of the rock. So the three types of weathering will be taking place in the upper course of a river, and that is especially because these areas here tend to have lower temperatures due to the altitude, so the height or the relief of the land causing the temperatures here to vary sometimes, to freezing, or to change, to vary to freezing during the night. Then we also have mass movement taking place here. So some of the unconsolidated material is likely to be moved down the slopes, and that can happen in the form of landslides and mud flows. And this will happen where rock fragments are moving very fast, down slope. However, these here are not necessarily that common in the UK as in the landslides and mud flows, but what is a little more common is soil creep. And this here will happen during times of heavy rain, and that heavy rain will dislodge the soil particles and cause those soils to flow down the slopes in the upper course of a river. So the Bradshaw model helps to explain how the characteristics of a river are going to change as that river flows downstream. So we've seen that it starts in upland areas and eventually ends up in lowland areas. Now, the first 5 characteristics shown on the model here show an increase, right? So if you look from this end here, this here is increasing, and we are referring here to the discharge of a river. And the discharge of a river refers to the amount of water that river is carrying. So that means that the amount of water in the river will increase as it flows downstream. Now, at the source, the amount of water in the river will be a lot lower. And that is because the river is just starting off. And then as the river flows through the landscape, it's likely to be joined by tributaries or small streams which add more water into the river, and therefore the river water, and then you have other water that is coming in through processes such as infiltration, through flow, groundwater flow, and that increases the amount of water or discharge in the river. So that's one characteristic that increases as you go down the river. Then we also have the occupied channel width. So that is the width of the river, how wide it is. So in the upper course, it's likely to be narrow, but then as you flow down towards the lower course of the river, that river is likely to widen as it carries a lot more material and as it has more energy to erode that river channel. So it will eventually become a lot wider than it was when it started here. In the upper course. And then the channel depth as well is likely to get the depth will be deeper, or the river will become deeper as you flow from upstream to downstream areas. Okay. Then the velocity, so this is the speed of the water in the river, that will also increase, and that is because firstly the river will have a lot more water. We said it's collecting water through tributaries and small streams, but then also because it has more energy now that it has more water. It's also causing a lot of erosion to take place. And therefore, the channel of the river is not as rugged. It does not have as much material on the sides of that particular river channel, and therefore the flow of the water will be a lot smoother. And because there is less resistance from material that would be in the water otherwise, or would be in the channel otherwise, then it's flowing a lot more smoothly and therefore a lot faster. Then we have the load quantity. So load quantity here refers to the amount of sediment that is being carried by a river. And because it's eroding as it goes through, it's going to end up picking up a lot more material. It has more energy. It continues to pick up a lot more material. So towards the end of the river, it's likely to be carrying a very heavy load, which will be deposited towards the end there. Now we also have the last three here, characteristics that decrease as the river travels downstream. And that will be the load particle size, for example. So upstream here, it will be a lot bigger. So we know that the material that is likely to be flowing from the upper course is likely to be a lot bigger because it has not been through the processes of attrition, for example, and abrasion and so on. And as a result, the particle size will be bigger. But as we flow downstream, due to those processes of erosion, the material or the load particle size will become smaller. So from very big boulders, eventually to pebbles, and eventually to sediment as we get down here downstream. Then the channel bed roughness, we had mentioned that when we were talking about the velocity. So that is how smooth the channel is going to be. So it's likely to be a lot less smooth upstream and then become smoother as you go downstream. And then the angle or the gradient or the relief of the land is going to go from very steep to gentle sloping to almost flat towards the end over here. Okay, so that's a Bradshaw model showing how the characteristics of the river are going to change as you flow upstream to downstream. Okay, so what are the landforms that are created in the middle and lower course of a river? So we are going to be talking about meanders and oxbow lakes here. Now, the river will bend in the middle and lower course. And at this point, the river is flowing in a deeper and wider U-shaped valley. And that's because the river channel has been eroded due to the higher energy of the water. And that obviously is going to create a U-shape rather than a V-shape due to the lateral erosion that is taking place. Now, the water in the river will not flow in a straight line or does not flow in a straight line. Instead it flows in a corkscrew pattern, which is called the helicoidal flow. So it's going almost like in circles, and that will send the river's energy sideways, and that is what is actually leading to that lateral erosion that is taking place. Now, as that river water reaches the bends of the river, then it's going to cause the outer parts of those meanders, meanders as they are called, the bends in the river, to be eroded faster, because that is where you'll have the fastest current, or what is normally referred to as a thalweg. That is going to erode the outer parts, like you can see, like this particular bit here that is in red, that will be eroded faster, that there will be eroded faster, that is eroding faster, and so on. But then the inner part of the bend will have less energy, and the erosion there'll be hardly any erosion there really. If anything, it's deposition that is going to take place there due to the fact that the water there is flowing a lot slower. So what will happen over time is that the neck of this meander, for example, over here, you can see there's a neck here of the meander. Because you have faster erosion here, on the outer part of this bend and on the outer part of this other bend here, these two here are eventually, that neck of the meander is eventually likely to erode right through. And then when that happens, the river now will flow, it will cut through and flow in a straighter a more straightforward channel. So it will be a lot smoother and the water will be moved out of this area a lot faster. And as that happens, you will also end up with some deposition taking place on the sides, especially when the river bursts its banks. Deposition is going to take place on the outer part of the on the floodplain around here, and that is going to lead to this meander eventually being cut off. And when the meander is cut off, then you will have an oxbow lake forming over here. Now, other landforms that form in the lower coast will include levees, and levees obviously are embankments on the side of a river. Those will happen or form when the river is in flood. You will have the floodplain itself, which is the area that is around the river that receives that flood water, and will have sediment that will be deposited on it. So that's a floodplain. And then you will have deltas and estuaries, and those are areas of deposited material near the mouth of the river or at the mouth of a river. Okay, so those are other landforms that are worth mentioning here that are formed in the lower course of the river. So what are flood hydrographs and what are the factors that affect them? So a flood hydrograph is just a graph that shows us the changes that a river goes through due to rainfall. Now, as you can see here, we have a line, and this red line here is showing us the amount of water in that particular river. Okay. So you can see here that it starts off quite low. The amount of water is low. And the reason why it's low is because the rainwater has not yet reached the river. Now, these bars here, this B here, well, shown by B here, or labeled as B rather, sorry, is this bar here is the rainfall. And this here at the top part of this bar here shows us the peak rainfall. So that is the time when we have the most rain falling. Now that rain is then going to find its way to the river. And as that happens, the amount of water or discharge of the river will start to go up. And that is what we are referring to as the rising limb. So it's going to take some time for the water, obviously, to get to its peak discharge, or the maximum amount of, not maximum amount of water, but the highest amount of water from this particular rainfall event. And then that water is going to start draining away from that particular river and obviously draining towards the sea and the ocean. And that is what we are referring to here as the falling limb. Now, the other thing that is very important here to note is the lag time, which is labeled C over here. And the lag time is the difference between the peak rainfall, B, and the peak discharge over here. Now, the longer the water takes to get to the river, the less the flood risk. However, and that means that there will have been a longer lag time. However, if there is a shorter lag time, then it means that that river is at risk of flooding. And that is because the water will be reaching that particular river very quickly, and therefore that river is likely to flood. Okay, and something that we forgot to mention actually is that one side of one y-axis on this flood hydrograph here will show us the runoff or discharge in cumex, which is cubic meters per second. And then on this side here, it will show us the precipitation, which is represented by the bars here. And then on the x-axis here, we have the time. And in this particular case, it's shown by the days. So this is day 1, and that is day 2 over there. Now, there are several factors that can affect a flood hydrograph, and one of them is urbanization. Now, if you have an area that has a lot of buildings in it, it means that the water is not going to be able to infiltrate the tarmac and the concrete, and therefore will sit on the surface, and therefore you will have a shorter lag time because that water is going to flow through drains and through that surface runoff and get to the river very quickly. And so urbanization is likely to lead to a higher flood risk. Then we have deforestation as well, which is another factor that can affect a flood hydrograph. In places where trees have been cut down, there will be less interception, and therefore the water will go straight to the ground other than being intercepted by the leaves of the tree. And that again will lead to a shorter lag time, which is likely to increase flood risk. So in places where you have forest which have not been deforested, you're going to have a longer lag time. Okay, and then we have what is referred to as antecedent rainfall, and that is referring to rainfall events that have taken place previously to this particular rainfall event. So if you had a lot of rain prior to this particular rainfall event here, the ground is already likely to be saturated with water, and as a result of that, this new water that is coming through this new rainfall event is likely not to be able to infiltrate the ground as quickly, or as as quickly, yes. And as a result of that, there will be a lot more surface runoff, shorter lag time, and increased flood risk. And then you have afforestation here, which is a planting of trees. Obviously, if you plant more trees, you have more interception and therefore a longer lag time. Okay. Okay, so here we have our flooding case study, which is the Sheffield floods of June 2007. And I have summarized them here under two headings. So the first one here is the physical causes of the floods, then the human causes of the floods, and then eventually the impacts of the floods. Now, the first physical cause here is antecedent rainfall. And this is rain that falls before the actual rainfall event that causes the floods. So on the 15th of June, there was 90 millimeters of rain that fell in this particular area. Now, that 90 millimeters is equivalent to a month's worth of rainfall, and that left the ground quite saturated. And then 10 days later, on the 25th of June, there was another 100 millimeters of rainfall falling within 1 day. And that obviously could not, that new rainfall could not infiltrate the ground due to the ground being saturated, and therefore you had a surface runoff, very rapid surface runoff, and which led obviously to a short lag time and was one of the causes of the flooding. Then a second physical cause here is the relief of the land. So the height or the shape of the land here, or topography if you like, and Sheffield is surrounded by 7 hills, and these are quite steep, and that means that the water will run off those steep hills very fast as it moves towards Sheffield, which is located at the foot of the Pennines. Then we have the fact that Sheffield is at this particular area is at the confluence of 3 rivers. Now, a confluence is the point at which either 2 rivers meet, or a river meets, a stream meets the river, or a tributary joins the main river. And as a result of that, having 3 different rivers converging here, then there's a lot of water coming to meet in Sheffield and then following just one particular path. Now that obviously increase in water from the 3 rivers obviously as well led to this particular area being at risk of flooding. Then moving on to the human causes here, Sheffield is obviously heavily urbanized, and because of that, it means that there is less infiltration due to the concrete surfaces and the tarmac surfaces, and then the drainage around Sheffield was actually not sufficient to cope with the amounts of water that fell in the year 2007. And then also we are talking about poor flood defenses in this particular area, which also led to, were one of the contributing factors to the flooding. Now, moving on to the impacts of the Sheffield floods. 2 people died during those particular floods, and they died from drowning, unfortunately. And then 1,200 homes were flooded, 1,000 businesses affected, etc., etc. If you'd like to pause this particular slide and just read through those, please do. We'll move on to the next one. Okay, so this slide here is a summary of the flood risk management in Sheffield. and there are two main ways that Sheffield has tried to mitigate against flooding, and those are soft engineering and hard engineering. So we have different types of engineering that are shown here. You have flood walls, dredging, levees, and diversion channels, and each of them has benefits and risks as well, or limitations rather. So the first one here are flood walls, and these ones are built alongside the river, and they increase the water holding capacity of the rivers. Now the benefit of those flood walls is that they are cheap to build, and they are suitable for city centers and will protect them from flooding taking place. However, the limitation is that because the river has more holding capacity, that water that is being held is likely to flow to other areas very quickly and is likely to cause flooding further downstream. Then the second type of hard engineering is dredging, and dredging is where you dig up the excess sediment that is in the river and remove it from the river so as to increase again the holding capacity of the river. Again, the limitation here is that it needs to be done fairly regularly because sediment will keep on accumulating year on year. So you're likely to need to do it every year to ensure that holding capacity of the river is at a good level so that the river does not flood. And again, the risk here is that the limitation here is that it's likely to increase flood risk elsewhere because the river will be flowing a lot faster and a lot smoother. Then you have levees, which are raised embankments, and these again will increase the river capacity. Then diversion channels, and these ones here is where you divert the water from valuable areas such as city centers. The benefit of that obviously is that you're protecting the area, but again the limitation is that you can increase the risk elsewhere. So types of soft engineering, you have floodplain restoration here, and this is where vegetation and greenery is restored in an area to allow for more infiltration and interception. So you just basically plant more trees to ensure that you're reducing the flood risk. Then you have river channel restoration as well. And this is where you rebuild your meanders, and that ensures that the water is flowing a lot slower through the area. Then the banks are also lowered to allow water to flow to flood park areas, for example. And obviously all this here is at the same time increasing the natural beauty of the area and increasing its biodiversity.